Namaskar, friends. I welcome you all in this class of structural analysis. Today we are going to discuss the theorem of three moments. Friends, this is a quite old technique discovered in 1857, but it is quite useful today also. We can analyze the continuous beam which is indeterminate by this method. In fact, if a continuous beam is there and we have to find out the moments at the nodes, this is quite handy method we can use. So today we will discuss this method and we will derive the theorem of three moments. So let us discuss first the basic principles involved in this method. Friends, you can see this is a continuous beam shown in the figure, and you can see here the loads are there, and these two ends are continuous. So if we want to analyze this frame, this beam, this continuous beam, if we want to analyze this continuous beam, one of the method is that let us make it the beams simply supported and release the moments at these nodes, and then after releasing the moments on these nodes we can apply the unknown moments at these nodes and find out the effect. What will be the effect? The effect will be that if we have released the moments at these nodes, so the effect will be these beams will become simply supported and there will be rotation at these nodes because of these loads. But as you know that in a continuous beam there will be rotation, but the slope will be, there will not be any change in the slope at these nodes because this is continuous beam. Here we have introduced release after releasing the moment here, so there will be kink here and the continuity of the beam will break here. So to restore this condition we have to write the compatibility equation in such a manner that the relative rotation between left and right of this node is 0. So from this compatibility equation we will calculate the unknown moment at this node. That is why it is also called compatibility method of analysis. So in effect what we can doing that the above structure is equivalent to this structure plus this structure. So and again if the supports are also sinking, then we can also add up here and you can see that this is equal to this plus this plus this. So how it is I will explain you that we have introduced release at these nodes. This means that we have released the moments at these nodes. Now in the next step we will take the same structure and apply moments at these nodes. Say M1 here, M2 here in the left, and same M2 will be at the right, and M3 here. suppose the nodes are 1, 2 and 3. So in effect what we are doing, that whatever moments we have released, we have applied in this structure, and if there are sinking of supports, say delta 1 sinking at node 1, delta 2 at node 2 and delta 3 at node 3. So this is going to be the two conditions which we are adding. So what will happen, because of these loads and releases introduced at these points, this beam will be deformed. So there will be a relative rotation between these two, between left and right part of this node. So if we draw a tangent at this point, this angle, say alpha, will be the relative rotation between these two parts, and because of the sinking of the supports, there will be a rotation of angle beta. So friends, you can see this alpha and beta are in opposite directions, so you can say that the net deformation will be, or rotation will be, d is equal to alpha minus beta. Now what should have been happened, if it is a continuous beam, there should not be any relative rotation between the left and right part of this node. So this d should be nullified because of these moments m1, m2 and m3. So because of m1, m2 and m3, the relative rotation at this node 2 plus the rotation because of these loads on simply supported load and sinking of supports d, the sum of all should be equal to 0, because there is no relative rotation at node 2 in the continuous beam. So this is the compatibility equation we will use to find out the value of m2, m1, m2 and m3. So friends, let us see one more thing I want to tell you here, that because of these m1, m2 and m3, the unknown moments coming at these nodes, and we have to find out rotation at this point, we are going to use the flexibility coefficients which we have already discussed in previous class. So I will again explain it, that how we are going to use the flexibility coefficients which are also used in the force method of analysis. So if what we will in effect find out, that if a unit moment is given at this point, what will be the rotation at this point, so that we will call it, if this is node 1 and this is node 2, so F21 will be the rotation at node 2 because of unit moment given at node 1, so that will be called F21. And if moment here is m1, so actual rotation because of this m1 will be equal to m1 multiplied by F21. Similarly friends, what will be F22? F22, say left, because on the left side of this node and on the right side of this node the rotations will be different, and we will call it F22L and F22R. So what is F22L? F22L is rotation at node 2 in the left part because of the unit moment given at node 2. Again F22R is equal to, is defined as the rotation taken place in the right part at node 2 because of unit moment given at node 2. So this will be equal to F22R, and so the rotation here at node 2 because of this moment M2 will be equal to M2 F22 left plus F22R. So this will be the rotation because of this moment. Now let us calculate what will be the moment because of this unknown moment M3 here. So we will calculate F23. What is F23? F23 is the rotation at node 2 because of the unit moment given at node 3. So the rotation because of M3 at node 2 will be equal to M3 multiplied by F23. So friends, our equation becomes that D plus all these rotations taken together will be equal to 0. So this is the compatibility equation we are going to derive, and we will use this compatibility equation to find out the values of M1, M2 and M3. Now let us calculate the values of F21, F22L, F22R and F23. So friends, this is this is our simply supported beam, and this is node 1, this is node 2, and we have applied here unit moment at node 1, and we have to calculate the value of rotation, this rotation theta. So theta will be equal to value of rotation because of this unit moment applied at point 1. So this will be our F21. So we will use moment area method, which we have already discussed in our previous class, to calculate the rotation at this node. So friends, you can see here that if we draw a tangent at this point, this is going to meet, if we take vertical line from node 1, so this is going to meet here. Let us call this point P. So what is this? This is T12. In the moment area theorem, we have already studied that if we want to find out the value of tangential deviation of point 1 from point 2, this will be equal to the static moment taken about 1 of the M by EI diagram drawn for this structure. So this is the moment area theorem we will use to find out the value of T12. Why are we interested to find out the value of T12? Because if we have to calculate the value of theta, it will be equal to this T12 divided by this length. Say this length is L1 and its moment of inertia is I1 and E is constant. So if we are interested in finding out this theta to calculate the value of F21, we will have to first draw the bending moment diagram. Now you can see here, if unit moment is being given here and the value of this moment will be 1 at this point, and if we are drawing M by EI diagram, it will be 1 by EI1. Why the value of this moment? Because of this is simply supported beam, there will not be any moment at these points. Since we are giving here additional unit moment here, so the value of moment will be 1 here, and because of this moment, if we calculate from the simple statistics the value of reactions, so because we are giving in the clockwise direction this moment, so the reactions will give the anti-clockwise moment in this direction and this directions, and its value will be equal to 1 divided by L1. Why 1 divided by L1? Because taken together the moment at any point, at this point or this point, should be equal to 0. So 1 by L1 multiplied by L1 will be equal to 1, and this is in opposite direction of 1. So to nullify this effect, the value of reactions will be 1 by L1 this side and 1 by L1 this side, and there is no other vertical force, so these will be equal and opposite. You know from the simple statics that the sum of the forces in the vertical direction should be equal to 0. So from this we can calculate this diagram, because the value of moment will be here at 0 at point 2, and value of moment at 1 will be equal to 1. So if we are going to draw the M by EI diagram, this will be our M by EI diagram, where this length is L1 and the material property is EI1. So if we want to find out this T12, the value of T12, so T12 will be equal to this length will be equal to the moment of static moment of this M by EI diagram taken about point 1. This is point 1, this is point 2. So first let us calculate the area of this triangle. This will be half multiplied by base L1 multiplied by the perpendicular, that is equal to 1 by EI1. Okay, so this is the area multiplied by the centroid of this triangle. Centroid of this triangle will be at a distance of L1 by 3, as you know from simple geometry. So this will be equal to L1 divided by 3. So this will become 1 by 6 L1 square by EI1. Now if we have to calculate this angle theta, which is equal to F21, that will be equal to T12 divided by L1. This value T12 divided by L1, because this angle is quite small as compared to the length of the beam, so we can write theta equal to T12 divided by L1. So this will be equal to L1 square divided by 6EI1 into L1. So this L1 will be cancelled out and it will become L1 divided by 6EI1. Friends, in our earlier class we have already derived this equation that if we want to find out the flexibility coefficient, this will be equal to L1 divided by 6EI1. So let us write it down that this is our F21. Now what next we have to calculate? Next thing we want to calculate, we have this is node 1 and this is node 2. Node 1 and node 2. So friends, we have already seen that if we apply a unit moment at this node, what will be the value of rotation at this node in the earlier slide. In this slide we are going to calculate that if we are going to give unit moment at node 2, what will be the rotation at node 2, this theta, and this theta will be equal to F22L. As I have already explained why we are taking L here, because at node 2 in its left there is a beam, again in its right there is a beam. So when we will give a unit rotation in the right side and calculate the rotation because of that moment, that will be called F22R on the right side of the node 2, and on the left side of the node 2 we are nomenclaturing is as F22L. So again we will use the same moment area method to calculate this angle theta, because as we know this length is equal to T12, and we can calculate T12 from the moment area method. The value of the moment of M by EI diagram taken about 0.1. So in this case what will be the M by EI diagram? From the earlier one there is a little change here. You can see that in this M by EI diagram the value of moment is 1 by EI1 at this, because we are applying unit moment here, and because of the same logic the moment here will be equal to 0. So this will be a triangular M by EI diagram, and again its length is L1 and material property is EI1. This is node 1 and this is node 2. So what will be the value of T12? That will be equal to the area of this triangle, half multiplied by L1 multiplied by 1 by EI1 multiplied by the centroid of this triangle from node 1, and that will be equal to 2L1 by 3. As you know from simple geometry that this distance centroid of this triangle from this node will be equal to 2 by 3 of its base. So let us multiply it by 2 by 3 L1. So this 2 will be cancelled out and its value will become L1 square divided by 3EI1. So friends, we have calculated here T12. Now again we can calculate the value of theta, that is equal to F22L, that will be equal to T12 divided by L1. This T12 divided by L1. So this will be equal to L1 square divided by 3EI1 into L1. So L1, this one L1 will be cancelled out and this will be equal to L1 divided by 3EI1. So friends, you can see here that F22L is equal to L1 divided by 3EI1. Now we have calculated F21, the unit moment applied here at node 1 and the value of rotation at node 2. We have calculated the value of F22L, that is the unit moment applied at the left side of the node 2 and the value of rotation at the left side of node 2. Now we are going to calculate F22R. So friends, this is node 2 and this is node 3. So now we are applying the unit moment at the right side of the node 2 and we have to calculate the value of rotation at the right side of the node 2. So this theta will be equal to F22R according to our notations. So again we will apply the same principles of moment area method to calculate the value of F22R. First we will draw the M by EI diagram. You can see since we are applying the unit moment at this node 2, so the value of moment here will be 1, and if we divide it by EI, say the value of the length of the beam is L2 and moment of inertia is I2, so this will be equal to 1 divided by EI2. This is node 2 and this is node 3, and this length we will call it T32, tangential deviation of 3 from 2. So this is equal to T32, and we are going to calculate the value of T32 again using the moment area principle, that will be equal to the moment of this M by EI diagram taken about point 3. So what will be the, let us calculate the area of this diagram first. Half multiplied by L2, the length base, and multiplied by the ordinate, perpendicular ordinate, that is equal to 1 by EI2, multiplied by the distance of CG of this diagram from node 3, and that will be equal to 2 by 3 L2. So we will multiply it here, 2 by 3 L2. So this 2 will be cancelled out, and this will be equal to L2 square by 3 EI2. Now for calculating the theta, that is equal to F22R, this will be equal to T32 divided by L2. This T32 divided by L2, length of the beam. So that will be equal to L2 square divided by 3EI2 divided by L2. So this L2 will be cancelled out, and F22R will be equal to L2 divided by 3EI2. So friends, we have already calculated F22R. Now the next we are going to calculate is the rotation at point 2 because of the unit moment applied at node 3. So that will be called F23. So this is our node 2 and this is node 3. And we have already done this. So we don't have to apply moment here, rather we are going to apply moment at this place, unit moment here, and we have to calculate the rotation taken place at node 2 because of the unit moment applied at node 3. So this will be equal to theta is equal to F23, the flexibility coefficient F23. And again we are going to use the same principle of moment area method. So we will calculate the value of T32, tangential deviation of point 3 from point 2, and that will be equal to the moment of the M by EI diagram taken about point 3. So the M by EI diagram you can see here, this will be equal to 1 divided by EI2, the length is L2, this is node 2 and this is node 3. So the value of T32 is equal to, first let us take the area of this M by EI diagram, that is equal to half multiplied by L2 multiplied by 1 divided by EI2, and then the center of gravity of this diagram, this distance from node 3, and that will be equal to L2 divided by 3. So multiply here by L2 divided by 3. So this will be equal to L2 square divided by 6 EI2. Now what will be the value of theta? Theta will be equal to F23, and that is equal to T32 divided by L2, which will be equal to L2 square by 6EI2. This L2 will be cancelled out, and F23 will be equal to L2 divided by 6EI2. So friends, you have seen that we have found out the values of flexibility coefficients. Now we will write down the equation as we have discussed earlier. We will write down the equation for this three moment theorem, and that will be equal to, if you remember, we had said that D will be equal to alpha minus beta. Alpha was the rotation because of the actual loading on the simply supported beam, and beta was the rotation because of the sinking of the supports. So the final equation was D plus F21 M1 plus F22L plus F22R multiplied by M2 plus F23 M3 is equal to 0. Now let us write down the values. So the value of F21, as you can remember, it was equal to L1 divided by 6EI1 plus M2 multiplied by F22L was equal to L1 divided by 3EI1 plus L2 divided by 3EI2 plus M3 multiplied by L2 divided by 6EI2 is equal to, we have taken D on this side, so this will be equal to minus D. Now friends, let us see what is equal to D and how we are going to calculate this. So D is alpha minus beta, and as you have seen, the what is alpha? Alpha because of the loading here and the loading here, the value of rotation at this node, and again there will be rotation here at node 2. So alpha was this angle, this will be equal to this angle plus this angle. So if we can write it as theta r and theta l, so alpha is equal to theta l plus theta r. And let us say that if we draw the bending moment diagram, because of the loading on the simply supported beam, which we can easily draw because this is a determinate structure, and in this you can easily draw the bending moment diagram because of this loading. So suppose this is our bending moment diagram because of the loading. Let us say the area of this bending moment diagram is A1 and the point of center of gravity, this distance is equal to x1. Again, area of this bending moment diagram is A2 and the value of center of gravity of this bending moment diagram from the right hand support node 3 is equal to x2. So from moment area theorem again we can calculate the value of theta L and theta R. What will be the value of theta L? Theta L will be equal to, if we draw the tangent here, this tangential deviation will be equal to A1 multiplied by x1. Okay, A1 x1, and then if we divide it by the length of this beam, so A1 x1 by L1 will be equal to theta L, and similarly theta R is equal to A2 x2 divided by L2. You can see here, if we draw a tangent at this point, this will become the tangential deviation, and that will be equal to the M by EI diagram, the moment of M by EI diagram taken about point this point. Let us write EI also, because this is M by EI diagram and if we are going to take A1 as the area of bending moment, then we have to divide it by EI1. Here also we have to divide it by EI2. So this will be the value of theta L and theta R, that is alpha. So alpha will be equal to A1 x1 divided by EI1 L1 plus A2 x2 divided by EI2 L2. Again friends, you can calculate the value of beta from this diagram. This is delta 1, the center one, it has gone by delta 2, and this is delta 3. So this is beta, this angle is beta. So beta we can divide it in two parts, this angle and this angle. So this angle will be equal to, what will be this length? Delta 2 minus delta 1 divided by L1. This is distance L1. So this angle will be equal to this much, and again this angle we can calculate, this will be equal to this length divided by this length. So this length is delta 2 minus delta 3 divided by L2. So friends, beta is nothing but the addition of these two angles. So we can write it down here, that beta is equal to delta 2 minus delta 1 by L1 plus delta 2 minus delta 3 divided by L2, and this completes your equation because you have calculated the values of all the coefficients and the alpha and beta. So friends, this is how in this equation we can calculate the values of flexibility coefficients and the values of rotation using the moment area theorem, and this equation provides you a compatibility equation. You can write down such equations for all the consecutive nodes taken two beams together at a time, 3 nodes and 2 beams. If you write down these equations, if there are n nodes, you will have n minus 1 such equations, say n minus 2, and you can calculate the values of all the n minus 2 intermediate nodes moment from these equations. Thank you very much.